Section 2. Get to the right page here. You may or may not remember that when I was recording Section 1, I got into it and started looking at some stuff and said, you know, I kind of think I revised this. Is this the newest version of the handout? So turns out I was thinking of a different course. I made some changes for Physics 122 for the most recent time I taught it, this past spring. But the last time I changed this course turns out to have been 3 years ago. So everything was good. I was showing you the most recent version of the notes, just like I should. And so Section 2 deals with, among other things, vectors. Start out with the definition. Well, two definitions. Physics is all about measurable quantities and trying to find the relationships between them. And these measurable things come in two varieties called vectors and scalars, and the difference between them is whether or not they have a direction. So some examples. Force is a vector. If a force again means a push or a pull, if I exert a force of 1 pound on this box toward the east, it doesn't do the same thing to the box as a force of 1 pound toward the north. If I want to completely describe how I was pushing on the box, I have to give its magnitude and direction. Force is an example of a vector. I've got velocity on the list there. If you're in your car driving 30 miles an hour toward the east, that's not the same thing as driving 30 miles an hour toward the north. The car is moving in a different way. Velocity describes how something is moving, how its position is changing. And there's lots of other things we could put on a list, and we'll encounter a number of them before the course is over. On the other hand, some things do not have a direction. We call them scalars. Anytime you count something, the number of atoms in an object or the number of eggs in a carton, or so, that's just a number, and that's all there is to it. Temperature. There is no difference between, if it's 71 degrees Fahrenheit in this room, it's not like 71 degrees toward the east is different than 71 degrees toward the north. There is no east or north, it's just 71 degrees. Time is a scalar. If I've been talking about this for 3 minutes now, again, there isn't any east or north to that. So some things are vectors, some things are scalars. Most people don't have, slid off the top of the picture, didn't I? Most people don't have too much problem. Did the camera move? I think the camera got slid. Okay. Most people don't have too much problem with the definitions. Where it gets a little trickier is in doing the math, or vector math in particular. Scalar arithmetic, that's drooping again. I don't think I've got one of these clamps tight enough. Let's see if that behaves. Scalars are just ordinary numbers. You've been teaching, people have been teaching you scalar arithmetic since kindergarten. 2 + 2 is 4. And that's about all I have to say about scalar arithmetic. A vector is not a number. We'll see there's a couple of different ways of representing it, but a good way of thinking of it is to think that a vector is an arrow, okay? How long, well, like down here at the bottom of the page, how long the arrow is represents the magnitude of the vector. If a car is driving 60 miles an hour, you might represent that with an arrow twice as long as the velocity of some other car that's going 30 miles an hour. And then which way the arrow points, of course, would be the direction. So a scalar is not a number. that can be represented by a group of numbers, 2 numbers if you're working in 2 dimensions, 3 numbers if you're working in 3 dimensions. But well, let's start out thinking of them as arrows anyhow. And so how do you add and subtract and do various operations like that with an arrow? Well, let's just jump right into an example. I think it's easiest to explain why you do the things you do if you start out with displacement vectors, and then after that, I'll just say a vector is a vector. They all obey the same rules. So let's consider the displacement of a bird. Run through that, and then I'll come back up to this and try and generalize what I've done. But just to start with the specific. So the bird's sitting on a branch, and it flies 50, decides that other branch over there looks better for some reason, flies 50 feet horizontally, lands on that branch. And, well, maybe that wasn't such a good branch after all, and it gets off the branch and flies 20 feet up to land on the peak of a roof. And the view is kind of nice from there, but it decides it doesn't really want to do that either. So then it goes right straight up another 30 feet and decides it wants to sit on a wire that happens to pass over this building. And so it also says what direction it went in each time. So the question is, what one single displacement would have had the same effect as the 3 that this bird went through? That's what finding the resultant of some vectors means in general, whether they're displacement vectors or velocity vectors or force vectors or, you name it. What one single vector would be equivalent to this group of vectors you have acting together. In this case, what one displacement would get the bird to the same place? Well, the simplest way to do it from a conceptual point of view, not the simplest way to do it from a convenience point of view, but with the least sophisticated thing to do would be just to climb up into the trees with a tape measure. And well, the bird started here and it went over there, and yeah, that would be a pretty awkward way to try and conduct a quiz in a physics class. So you could accomplish the same thing if you drew a little miniaturized picture of what was going on instead of actually climbing up into the trees themselves with a tape measure. And that's what I've done on the bottom half of this page, okay? You have to pick some scale that's going to fit conveniently in the amount of space you've got available on your paper. And in this case, and these actually were drawn to scale. I'm pretty sure I've got a ruler here. It's not a very good ruler. I just happened to be handy. This end of it's great, but it's an old ruler from the lab and somebody broke it. And instead of throwing it away, I just took it home and it was handy, so I grabbed it. So see, a 50-foot displacement is, well, okay, it turns out when this was duplicated, it didn't come out quite full scale, did it? But on the original, when I first drew all this, that was exactly 5 centimeters long. So imagine it's 5 centimeters long. So this is a literal picture of what the bird was doing, except I haven't gone to the trouble of drawing all the scenery in the background. I didn't draw the tree branch here, and I didn't draw the peak of the roof over here, and I didn't draw the wires up here. But if you can imagine all that stuff there, and I'm just drawing on a picture of where the bird was. First, the bird flew from here to here. And then it landed on the branch. Thought about it for a little while. Next thing, the bird got off the branch and flew from there to there, which is where the peak of the roof was. And it sat there for a while. And then you see that each of these is each picture here is a later stage in the process of solving the problem. First you draw that, next you draw that, next you draw that. And up here is where the wire is that the bird finally ended up at. Okay. And this has to be all drawn to scale, not only the length of the arrows, but the directions also. I thought I had a protractor here somewhere. Hold on. Okay, that was one of those things where I look around for a while and finally realize it's in my shirt pocket. This is kind of a little protractor. I've got some bigger ones in the lab that are kind of better than this, but if I get it lined up right, yeah, that's about where it belongs. Well, you can't read it really super accurately. You'd have to take a ruler and extend the line on out to where the numbers are, but that looks kind of 35 degree-ish on there. So anyhow, both the lengths and the angles have to be drawn to scale. And then the final step is to say, okay, the bird did this and then did that and then did the other thing. And if it could have just figured out where it wanted to go in the first place, it would have started here and gone right straight to there, kind of like that. So to get the answer to the question then, this is solving a problem by constructing a scale drawing. Later on, we'll get to how to solve these types of problems with your calculator, but this is a ruler and protractor solution. There is at least one problem in the homework for this section that is supposed to be done with a scale drawing like this. Could possibly come up on the quiz. So if you don't own a protractor, if you're coming in to see me face to face, I can loan you a protractor from the box full that I've got in the lab. If you're doing this entirely remotely from home, you may need to buy a protractor, even though you're only going to use it a few times. Fortunately, protractors are cheap. You can probably get one. I would think they probably got them at Walmart and various other stores sort of like that. Anyhow, you measure how long this is with the ruler, and it's supposed to be 7.8 centimeters long. Well, like I said, it didn't get reproduced to quite exactly the right size. That's looking more like 7.5 than 7.8, but it was supposed to be 7.8. And so 7.8 centimeters on the drawing represents 78 feet in the real world, because that's the scale it was drawn to. And then what direction should the bird have flown in? Well, you put your protractor on there, and it goes right there like that. And well, that's kind of looking more like 33 degrees than 32. But in a perfect world, that would be 32 degrees, and that's how you get the direction part of the answer. And actually, that's a good point. I should mention that. If this does come up on a quiz or on your first exam, I don't expect these scale drawings to be perfect, okay? To be perfectly honest, when I'm preparing something to show to a class, I always calculate the answer and then make sure that the drawing comes out right. If I did it the way you're actually, you know, if I solved it by purely graphical methods without also calculating the answer, I would be slightly off. It's unavoidable. It's better if you draw it bigger, okay? I wouldn't be as far off if I drew it so it filled the whole page or close to it. I'd be off by more if I made some tiny little thing, you know, like that big. Because if you're off by a millimeter out of that much, that's a 10% error. If you're off by a millimeter out of that much, that's only a 1% error. So draw them as big as will fit in the available space if you're doing a scale drawing solution. But if you are fairly close, I'll give you full credit. Like if this was a question on a quiz and instead of 7.8, it came out maybe 7.7 at, I don't know, 34 degrees. Yeah, I'd probably give that to you full credit. Any further off, if you had like 35 degrees, I'd probably take off a little bit for sloppy measurement. But I don't expect scale drawings to be perfect, dead-on things, because you're always a little bit off reading the ruler and you're always a little bit off reading the protractor. So let's take what I just did and try and generalize it to a step-by-step procedure for any kind of vector. And that was back in the middle of the previous page. So head to tail method, so called because you see each time you draw the next vector, you put the tail of the new one on the head of the one you just finished drawing. So a graphical solution using the head to tail method. Draw an arrow for each vector. Like I've already said, the magnitude is represented by the length of the arrow and the direction by the direction that you draw it. So each of the vectors being added, you draw one after another with the head of the next, or the head of the previous one on the tail of the next one. Then draw the resultant from where you started to where you ended up, from the tail of the first one to the head of the last one. And whether it's displacement vectors or force vectors or anything else, that's how you can add vectors with a scale drawing. Back to page 6. Notice, and hopefully I mentioned this in section 1 also, well, this part of it I'm sure I mentioned in section 1, a complete answer includes the correct units. If this was a quiz and you just said 78 at 32 degrees, I'd knock off half a point. I'm sure I said that when I was going over section 1. Units matter. The other thing that I didn't get into in section 1, because I wasn't covering vectors in section 1, is the complete answer includes both the magnitude and direction. If you just simply said the resultant is 78 feet, well, that's the significant chunk of the answer you've left off there, and that would cost you more than the half a point that I would knock off for no units. Probably 2-3 points or something. I mean, I would give you a lot of the points just for correctly drawing the head-to-tail diagram, but then knowing how to read the answer off the diagram counts for something also. So anyhow, here is an example for, well, an example for you to try, but I need to explain something first before you pause it and try to do it. So once again, you've got two vectors. The question is to find the resultant of them, which means, in this case, they're forces, okay? Well, I said it's two people pushing on a table, but a box of staples is what fits. It's really handy. My wife left this box of staples sitting here. I've used it as a prop several times already. So you've got one person pushing in this direction with a force of 10 newtons. A newton is a metric unit of force equal to a little bit less than 1/4 of a pound, and I'll give it a more precise definition in another week or two. But for now, let's just say a stick of butter weighs roughly a newton, and that can be our working definition for today anyhow. So 10 newtons, about 2 1/4 pounds. Somebody's pushing on it like that. At the same time, somebody else is pushing it in this direction with a force of 15 pounds. So two forces acting at once, something sort of like that. And the question is, what one single force pushing sort of in that direction would have the same effect on the box as these two acting together? What one force is equivalent to those two acting together? Well, you can find the answer by doing the same thing I just talked about on the previous page. You have to pick some scale, like a centimeter equals a Newton, and represent each force with an arrow drawn to that scale, and you put them head to tail. Now, the thing I need to explain here is that unlike these displacement vectors with the bird, this picture you've been presented with here does not show the vectors head to tail. They kind of, the natural way to draw these is more like tail to tail. You know, somebody's pushing that way, somebody else pushing that way. But vectors have a property called parallel displacement, which means you can move them around the page any way you want to, as long as you keep them parallel to their original direction. So if you've got a vector that points that way and another vector that points that way, the idea of parallel displacement means you can take that one and displace it across the page like that, as long as you keep it parallel to the direction it originally pointed. You can slide it over and you can put it there. And now the vectors are head to tail, and you can draw the resultant from there to there. And that's, I think, the rest of what you needed to know to try this yourself. So when we do this in class, I always have my box of rulers and my box of protractors there. And if you weren't exactly prepared for this and don't happen to have a ruler and a protractor, well, maybe you want to pause it here for a really long time, like long enough to go to the store and buy a protractor. Maybe you need to buy a ruler too. But however long you've had the thing paused, I'm going to assume you have now worked on this question yourself and show you the correct answer. I've got it. Well, there's the correct solution all drawn out to scale. But just to quickly go through how you would do that, you have to pick a scale, and for these particular numbers, 1 centimeter equals 1 Newton would work pretty well. So first you draw this thing 15 units long, 15 centimeters or 15 inches or 15 half inches, which would be 7.5 inches, or whatever scale you choose. That one was horizontal. The other one is right straight up toward the top of the page. So you draw that one next. When you draw the second one, you draw it coming off the tip of the first one. And you make that one 10 units long. And then after you've drawn those, you draw the resultant from the tail of the first one to the head of the last one, okay? From where you started to where you ended up. Something sort of like that. And then once that's all drawn, let me go to my, because that was just a quick sketch, which isn't really good for very much. But this one I don't think got shrunk in being copied. I think this is actually, yeah, that's really 15. And that's, well, I might be off by a millimeter. These things happen. But it's pretty 10-ish. So you draw that, you draw that. To get the answer, you measure the length of the resultant with your ruler. And I think you can see that came out just about exactly 18. Might be 18.1. But that's where I got the 18 from in the answer here. And then for its direction, I put the protractor on there. I buried the protractor under a bunch of other papers. There it is. And Yeah, that's, well, let's see, it belongs over there. Well, that kind of looks like 33 degrees rather than 34, doesn't it? Well, like I said, these things are always a little bit off. But that's the idea anyhow. That's how you get the answer off the diagram. And let's continue down the page. You will definitely need to do that yourself during the lab. And as I said, there's a possibility for a quiz or on the first exam that you might have to do that. So what if you wanted, instead of determining the answer off of a scale drawing method, what if you wanted to calculate it instead? Well, notice we have here a triangle. And the branch of mathematics that deals with triangles is trigonometry. So before we get into how to, well, maybe I should just throw in a couple comments about why you would want to solve it mathematically. It may be fairly obvious to some of you, but first of all, it's not going to have all these measurement errors in it that I've been whining about at great length for the last, I don't know, half hour or however long I've been doing it. You can, as many decimal places as your calculator can handle, which is usually quite a few more than you actually need. So there's the accuracy issue. Plus, instead of just whipping off a sketch like this, if you're trying as carefully as possible to construct a diagram, that takes a little time. Once you get good at the analytical type approach, it might actually be quicker than a scale drawing also. And of course, we're not really going to get into this in this course, but you get into three-dimensional problems, and what are you going to do? Build a model out of pipe cleaners? I suppose you could, but nobody does. So let's take a look at the background math that you need to do this sort of thing. Hopefully it's a review from some math course that you took earlier. If not, well, hopefully you're a quick learner. But the relationships dealing with triangles that we're going to need in this course, first of all, the trigonometric functions. The trig functions are ratios between the lengths of the sides of a right triangle. Let's start with the names of those sides. A right triangle, first of all, is a triangle that contains a right angle, okay, a 90-degree angle. The side that's across from that 90-degree angle is called the triangle's hypotenuse. The two sides that make up the 90-degree angle are called its legs. If you kind of focus in on one of the acute angles, it's like I'm really interested in this angle here, then if you select one of the acute angles like that, then you can distinguish between the two legs. The one that's on the other side of the triangle from where that angle is called the opposite leg. And the one that makes up part of that angle, represented here by the Greek letter theta, that's the adjacent leg. So let's say you wanted to know the tangent of 30 degrees. What does that mean? Well, it means the ratio of the opposite leg of the triangle divided by the adjacent side, okay? So even though this is obviously not what actually happens, you could imagine that living inside your calculator is this little bitty guy about a 1/16 of an inch tall, and in there with him, he's got all these little rulers and protractors and a lot of paper. And so when he receives the message that you want to know the tangent of 30 degrees, he draws a 30-degree angle. Okay, so just as a quick sketch, again, should use a protractor and make sure that's 30 degrees. Looks like I might have got it a little on the big side, but just for the sake of argument. Gets his protractor, draws a 30-degree angle, and then draws the third side perpendicular to this one to complete a right triangle. And then, now it doesn't matter how big he draws it, because if he drew it only that big instead, well, if this side, you know, if that is only half of that, which isn't quite the way I drew it, but just play along. If this is half of that, this will also be half of that. And when you divide them, you're still going to get the same ratio. Okay? So as long as he draws a right triangle with a 30-degree angle in it, it's all that matters. So draws the triangle, gets out the ruler, and maybe this side of the triangle comes out 1 millimeter long because, you know, remember, it's just a little tiny guy in order for him to fit inside your calculator. And this side of the triangle comes out 1.73 millimeters long. And then he divides the length of this one divided by the length of that one, and it comes out 0.577. And that's what the tangent of 30 degrees means. And if you ask for the sine of 30 degrees, that would be, for example, the opposite over the hypotenuse. So that would come out 0.5 even, and so on. And so that's the definitions of the trig functions, sine, cosine, and tangent. That's what they mean. The other relationship that we're going to get a lot of mileage out of that has to do with right triangles is the Pythagorean theorem. Square the hypotenuse equals, if you square this leg and you square that leg and add them together, it equals the square of the hypotenuse. C squared equals A squared plus B squared. Okay. All of this is only valid for right triangles. If you have a triangle that looks like this, now that looks like it's about 120 or 130 degrees, none of this is valid. Okay. If you try and do something like A squared plus B squared equals C squared, for that triangle, it is going to fail spectacularly. For those of you who've gotten a little further into your math, you might be aware that there is a generalized version of the Pythagorean theorem called the law of cosines, but actually pretend I didn't even say that because we're not going to use that in this course. Just keep in mind, got to be a right triangle. Okay, that's the math review. Having done that, I can introduce the idea of the components of a vector. It is frequently convenient to think of a vector as being the sum of two other vectors, one parallel to each of your coordinate axes. So X and Y here just stand for two convenient directions that are perpendicular to each other. With the bird in that example I did a little while ago, X and Y might stand for horizontal and vertical, for example. Or if you're talking about navigating which direction your car is moving in, they might stand for east and north. Just two reference directions that are perpendicular to each other, okay? And so you've got some vector, one of the displacement vectors for that bird flying around, perhaps. He flew from here to there, and the question is, if the bird went perfectly horizontal, followed by the bird going perfectly vertical, how far would it have to go in each direction to get there? Okay, that's what the X and Y components of this vector that I named V mean. So a vector is the resultant of its X and Y components. Now, I should probably address the use of the plus sign here, because oh, like this one back here, what was the answer to that? 1510, and this was, length of the resultant was 18, approximately, rounded off to the nearest whole number. It's 18 anyhow. And so people have a tendency to look at this sort of thing like I wrote here and say, you know, when I was in first grade, 15 plus 10 did not equal 18. But we're not talking about adding scalars here, okay? Basically what we've done is we've taken a symbol that was conveniently already on the keyboard and repurposed it to stand for an entirely different operation, okay? This, you see, you can tell by the little arrow over the top of their names that these things are supposed to be vectors. So we're not talking about addition like 2 plus 2 equals 4. Rather, when it's written between some vectors like this, the plus sign means this head-to-tail operation that I was talking about a few minutes ago, okay? It's the vector sum. It's not, it doesn't mean just add up their magnitudes. It means add up the arrows, the whole vector, magnitude and direction. So this arrow equals that arrow added to that arrow is what I'm saying over here. So what I'm going to do, the notation I've used in these note packets is that the ones that are named with letters are ones that I want to run through for you to imitate when you do the ones that I've named with numbers after that. So I'm going to do this and I'm going to do that, and then it'll be your job to do this, which is kind of similar to, let's see, find everything. Now this one would be kind of similar to that one, and this one would be pretty similar to that one. So let me run through these first couple here. Talk you through them. Oh, let's have a clean sheet of paper. This is just, I have this psychological quirk where I seem to be unable to throw away paper that still has a clean side on it. If you come into the lab, you'll find I've got a whole box of clean sides there. If you ever need any paper, feel free to help yourself out of that. Anyhow, I should put that over there. Problem I called 2A. So a good way to start many different kinds of problems is with a picture. Maybe I should have this down here where we can look at it. In this case, well, what I want to do is kind of finish off this picture and make it like that. I've got this picture of my 20-meter displacement vector, but I want to include the X and Y components on the picture. And if I do that, it looks like this. So I've got the 20 meters and the X component. Its length is what I'll call Vx, V for vector, and call the Y component Vy, okay? And these are perpendicular to each other because X and Y are perpendicular, kind of by definition. And this is important because I'm going to use that stuff from the previous page about, you know, trig functions and all of that, and it's got to be a right triangle for that stuff to be applicable. And this was a 30-degree angle because that was given in the question right there. Okay, so the idea is I could have solved this with the scale drawing method that I went over earlier, but rather than invest 3 or 4 minutes carefully drawing this all out to scale and carefully measuring the angles and length off of it, what I do instead is I just take like 5 seconds to whip off a quick little sketch, and then I will calculate how long these sides would have been if I had gone to the trouble of drawing this to scale. Okay, so this idea of head to tail vector addition is always lurking in the background, whether you're actually using that scale drawing method or not. That's why we always start with it when you're teaching people about vectors. So now I've drawn this picture of a triangle. If you don't happen to remember the definitions of the trig functions, they are on the formula sheet. This is the kind of thing the formula sheet is for. So if you're in the middle of a quiz and you're sitting there going, oh, my math teacher said that there was that thing SOHCAHTOA about remembering the trig functions, but I can never remember how to spell SOHCAHTOA. So never mind all of that. Just look at the formula sheet, and on there it says cosine, in this case it's the cosine of 30 degrees, is equal to adjacent over the hypotenuse. So then, next step, look at the picture you just drew and notice, oh, wait a minute. No, that's right, never mind. Notice that the adjacent side is the x component, the thing I called Vx. We don't have a number for that yet, so the letter has to stand in for the number. Over here on the hypotenuse, I do have a number for how long that is, so I'll fill that in. And now I have an equation that I can solve for Vx. Okay, the thing to do next would be to multiply both sides by 20. If you want to be a little more step-by-step about it, you multiply that by 20 and you multiply that by 20, and you see 20 over 20 cancels there, and you know, it's just Vx times 1. And whether or not you know the cosine of 30 degrees, the important thing is your calculator knows that it's about 0.866. It keeps on going. It's not 0.866 exactly, but rounded off to, you know, the 3 significant figures. That's what it looks like. So you multiply that times 20, and it comes out 17.3 meters. That's the x component. To find the y component, well, actually, there's a couple of different ways of doing it, but what seems the most obvious to me is to just repeat the same procedure, except now I'll use sine instead of cosine, because now I want the opposite side instead of the adjacent side. So sine of 30 degrees equals look at the formula sheet, and that's what it says, except it's neatly typed. And you look at your picture, the opposite side is Vy, and the hypotenuse is 20. So just like before, multiply both sides by 20. And actually, the sine of 30 is one of the few that comes out even, instead of some decimal that goes on forever. Sine of 30 is exactly 1/2. Vy, 10.0 meters, and that's the other answer the question asked for. Okay, so given a vector's magnitude and direction, that's how you get its x and y components. And the other question that I wanted to run through with you is just this other way around. Given the x and y components, how do you get the magnitude and direction? So there's that one again. Find the magnitude and direction of the vector with these components. So once again, first thing you ought to do is draw a picture. So the question says that it's got an x, this time it's force vectors because they're measured in pounds. It says the x component is 10 pounds. So draw that in the x direction, pointing toward the right. And it says the y component is 5 pounds. So you draw that pointing in the y direction. The vector that we're looking for is the resultant, the vector sum of these components. A vector is the resultant of its components. So I lay them out head to tail and then draw the resultant from the tail of the first one to the head of the last one. I could call it V for vector, or I could call it R for resultant, but I was in the mood to use F for force. Name doesn't really matter. The Greek letter theta for an angle is fairly traditional, although if you want to call it like A for angle, you could do that, I suppose. So once again, the idea is I have drawn my head-to-tail vector addition, kind of reminiscent of this thing, but instead of taking 5 minutes to carefully lay it all out to scale and carefully measure the answer off of it, I take just a few seconds to whip off a little sketch and calculate what these things would have been if I had gone to the trouble of drawing it to scale. So to get the magnet, and again, there's more than one way of doing this, but the first thing that comes to my mind as far as how you would get the magnitude, the length of the hypotenuse, is the Pythagorean theorem. C squared equals A squared plus B squared, or F squared equals 10 squared plus 5 squared in this case. And then you just crunch through the math. 10 times 10 is 100. 5 times 5 is 25. And then to solve it for F, you have to take the square root of both sides of the equation. Square root of 125, well, that's another number that kind of goes on forever, but rounding it off to 3 significant figures, I think I mentioned last week that 3 significant figures was going to be the standard that we used in general in this course. There might be a few exceptions now and then, but not very many. So that's the magnitude. That's half the answer. Remember I said earlier, if this is a quiz and you stop here, you're going to lose several points because there's another whole calculation to do to figure out the angle. So for the direction, well, I decided to use the tangent. Tangent is opposite over adjacent. So you look at the picture. The opposite side of the triangle has a length of 5, and the adjacent side of the triangle has a length of 10. Now, actually, now that I know the hypotenuse, I could have used any of the trig functions. I could have used sine, I could have used cosine. It wouldn't really make any difference. I'm just in the habit of using the tangent because if I happen to do the angle first, before I calculated the hypotenuse, this would have been the thing I had to use. But since we know the if you have this really strong emotional attachment to using the cosine instead of the tangent, well, you might as well. I mean, that should lead to the same answer also. So we know the tangent of the angle is 0.5. But the trouble is we don't want to know the tangent of the angle. We want to know the angle itself. How many degrees is that thing? Well, we need to manipulate this so that it says theta equals something rather than tangent of theta equals something. The way you get rid of a function when you're solving an equation, the way you get rid of a function is to hit it with its inverse function. Same sort of thing we did over here. The way you get rid of a square is to take the square root of both sides. The way you get rid of a tangent is to take the inverse tangent of both sides. The inverse tangent, I guess I didn't explain that on the bottom of the previous page, but the inverse functions just mean you go the other way around, okay? Tangent of theta, or tangent of 30 degrees is 0.577. The inverse tangent, or arctangent as it's sometimes called, the arctangent of 0.577 is 30 degrees. So if you start with the 30 and you're trying to get to the 0.577, that's the tangent. If you start with the 0.577 and you're trying to get to the 30, then that's the inverse tangent. On your calculator, it's second function tangent, or, well, that's not all calculators use the same notation, but that's probably the most common way of labeling it. If you have any trouble figuring out your calculator, let me know and we can talk about it. Hopefully it's not one of those enormous calculators with like 175 buttons on it, and I don't entirely understand how to use those either. But anyhow, the point is, a function gets canceled out by its inverse function. Just like a square root cancels out a square so that you're just left with the f over here, the inverse tangent cancels out the tangent so that you're just left with theta over here. And then for the other side of the equals, second function, different calculators, you have to enter things in different order. Some calculators, you put in the 0.5 first, and then you go second function tangent. Others, you go second function tangent first, and then you put in the 0.5. Hopefully you get that figured out. Once you do, you should be getting 26.6 degrees. Another pitfall is that some calculators by default are in degree mode, others are not. And you might end up accidentally calculating the inverse tangent of half of a radian instead of, or you might give me the angle in radians, thinking I started to say that backwards. The inverse tangent of 0.5 is probably somewhere around half a radian, maybe a little bit less, 0.4 something, or maybe it's a little more. Anyhow, that's fine as long as you label it as radians. But if you come up with 0.5 something and label it degrees when it's actually that many radians, that's not so good. So be aware of that too, that any time you use the trig functions on your calculator, you want to be sure it's in the right mode. So anyhow, putting it all together and presenting the answer as a nice tidy little package. The resultant is 11.2. This was measured in pounds. 11.2 pounds at 26.6 degrees. Magnitude and direction. Okay, so here's where you're supposed to pause it and do these two problems here. And if you really end up needing a lot of help after you've watched me solve it, it's probably a good idea for you to go back and try it again. Keep at it until you can do it yourself. But I should stop talking so you can pause. And now I'm assuming you're coming back after the pause. And I should grab the sheet of paper where I've got the math all worked out ahead of time here. Okay. You know what, in the interests of saving time, rather than writing it out step by step, because I already did that once with some almost identical problems, here's the solution to this one. So start out drawing the little diagram. You were given the, find the resultant mathematically. Now, again, the only reason that this approach works is because these two vectors happen to be perpendicular to each other. If you had been given a couple of vectors that made some other angle like that, I'll get to how you deal with that. Well, I mean, the scale drawing method works for a triangle like this just as well as it works for a right triangle. But as far as how you would calculate the resultant if your vectors are like this, I'm going to get to that in section 3. For right now, it's a good thing these two happen to be perpendicular, because otherwise none of this would have worked. So you draw the resultant and you draw the angle, and then you look at the triangle and apply the Pythagorean theorem to it. And when you work through all the math, that's what you get for the length of the hypotenuse. And then, just like in the example I did before, you use the inverse tangent of the opposite over the adjacent, 9 divided by 15, and that comes out 31 degrees. And then there's this one here, where you start out with the magnitude and direction, and you're supposed to find the components. Now, look carefully. I mean, at a casual glance, you might say, oh yeah, those are the two numbers I got. Look carefully and make sure this is the one you got for Y, and this is the one you got for X, because one fairly common mistake I see is people get sine and cosine mixed up with each other, and then you'd have this answer for this and this answer for that, and that's not good. So just like the example I did previously, it follows from the definition of sine that the opposite side equals the hypotenuse times the sine of the angle, and that gives you this. And it follows from the definition of cosine that hypotenuse times cosine equals the adjacent side, which gives you that. Okay, so now you are all experts on how to find the X and Y components of vectors. And I'm going, like I said a minute ago, I'm going to get back to the rest of the story of how to do vector addition in section 3. But for right now, let's get into how to apply what I've already covered to an applied situation, a practical problem. We're going to look at how to determine, basically, a projectile is something that's been projected, something that's been thrown. Somebody throws a baseball, somebody fires a cannon. And one of the more interesting questions about this is, where will it come down? You know, if you're firing artillery, it's nice to know ahead of time who you're going to blow up. So that's what the rest of section 2 is about. But we're just about to where I would usually take my middle of the period 10-minute break. So this is where I'm going to break off with this recording, and I'll make the second half of section 2 a second recording that you should find right next to this one in Blackboard once I've done it. But actually, I'm not going to do that right now because it's actually 7 minutes to 6, and I'm going to go eat my dinner and record the other half another day.